So we're looking at page 19, number 4. We need to use properties of cross product to calculate I cross K cross J. So I started writing out part of the solution here, I cross K, with the appropriate diagram so that we can try to apply the right-hand rule and see what flavor of J is gonna end up presenting itself. All right, the idea being that we're looking for a vector that's orthogonal to two other vectors. If those two vectors are along the x and z axis respectively, then necessarily the cross product vector would have to be along the j vector in some capacity, so positive or negative j, so along the y-axis, right? So what I would do here, and it's, you know, I don't know if this is any better than the hand waving I do in class, but if we could align our right hand rule, in this case the right hand, whether it's your actual right hand or the diagram I have here, so that we can get a sense of where the cross product vector would go, then we can get the result without ever having to go to GeoGebra or anything along those lines. Right? So I'm going to just kind of expand the size here. Now, what I can do based off of the technology that I'm limited to is I can get a sense of what A cross B would be in this context. All right, so we're looking at this vector here being my A and this one being the B. If that's the case, then A cross B would be going in this direction. All right, so then I just have to be thinking about, okay, well, what's A cross B in this context? All right, so A cross B, if this is my A and this is my B, going off in this direction this way, in the positive y-axis, would not be the result of I cross K, it would be the result of K cross I, right? Which is the exact opposite of what we want. Now, by the anti-commutative property, it tells us that in the opposite direction, we would have I cross K, all right? So K cross I has us going in the positive y direction, which puts us at J, whereas I cross K would have us going the opposite direction of that, which would be negative J. All right, so I cross K would be negative J. All right. A little mind bending, but if you can visualize it, it goes a long way. All right, and so when I was first learning this, I actually got a few pieces of PVC pipe, you know, the plastic pipe, plastic-ish pipe, and I put them together with a T connector, and I just marked it up. I'll throw in an image in this file later on, because I have it in my classroom right now. So it's you do what you can, and then once I got a good handle on it, I was able to move on from there. All right, so K cross J. All right, so it's kind of like, all right, well, let's take it back to go. So we start all over again, and it really, I mean, all over again? Not really. As long as you know where your bits and pieces are, your appropriate bits and pieces, then you're in good shape. All right, so get rid of that. We're starting off with a K and a J, so let me get rid of anything that's not a K and a J. Put the J down here. So now I know that I'm going to be moving in the direction of I, or at least on the I-axis, the x-axis in the direction of positive I, or maybe it's negative I. I just don't know which one. So then I get my right-hand rule involved. Now, this one again is it's so iffy because it's like, all right, well, I can't do based off of the way that this is formatted. I really have a hard time doing a K cross J. So what I can try to do is K cross J. All right, I'm sorry, J cross K. All right, so I would align it so that the A, the quote unquote A, is my J, and the B is my K. And I know the middle finger isn't pointing directly upward; it's kind of askew, but it's a fixed image, so doing the best we can, right? But if we follow that idea, that tells us that J cross K would put us in the positive I direction. So that means that I want to be going, if I want to go K cross J, I want to be going the opposite direction of that, which is going to be negative I. All right, so that's the one I want because it's the exact opposite of what my right-hand rule is giving me. All right. We make use of opposites here pretty frequently because it's a way of reasoning things out in ways that you might not otherwise recognize. All right, otherwise recognize. So now I have the results of the two parts here. So I'll clean it up, get some notation in here. So I know K cross J is equal to negative I. So as a result, I want negative J cross negative I. Okay, well, a couple of things I could do here. I could use my multiplication by a constant property to help out. I could also use the anti-commutative property by swapping the order and negating it. All right, so I cross J, each part negated, so I'm just doing a quick switcherooski here, negated by the anti-commutative property, but then I can factor out the coefficients here of -1, all right? So I would be pulling both of those out, so both of them coming on out, giving me a negative that's already there and two additional negatives. So result would still be negative. Then we'd have I cross J, which I think is a whole lot simpler to conceptualize. All right. So then if I go back to my ordinary coordinate axes, and instead of copying and erasing, I'll just redraw. I'd have I facing this away. J would be this away. Then by the right-hand rule, again, it's kind of hard to get at here, but if I'm applying the right-hand rule, the resulting vector, I didn't want to do that. The resulting vector would be in the upward direction. All right, that would be my K. All right, but that's something that you probably don't even need the right-hand rule for because IJ gives K as the orthogonal vector. That's the basis of the three-dimensional coordinate system. All right, so that part should have been all right. So we get a result of K here, bring down the negative, and that's your final answer. All right, so the result would be negative K. All right, so is this stuff that you could have done on GeoGebra? Absolutely. All right. The whole point behind these types of questions is to get you thinking about the three-dimensional coordinate system, not to bog you down with the minutia and have you spending a ton of time doing it by hand for the sake of doing it by hand. In fact, I'm never going to ask you to do it, using this technique on an assessment. I would be looking for the answer, but the goal behind these kind of questions is to get you that level of understanding so that it becomes more intuitive. All right. Find the magnitude of the cross products. That is much simpler because for these kind of questions, you don't need to actually find the cross product unless you want to. right? Because you could find the cross product between two vectors and then go from there. The benefit of doing it that way for a question like number 5 is that you could make use of unit vectors. All right, so I'll just show you really quickly. All right, so U could be thought of as 4 multiplied by 0, 1, 0, where V could be thought of as -3 multiplied by 0, 0, 1. So this would be the same as saying 4J, and this would be the same as saying -3K. All right, so if we cross those two, all right, so U cross V would be equal to 4J crossed with -3K. All right, so if we can figure out what J cross K is, we're only off by constant multipliers here. Fun fact, we already kind of figured that out in the last question. We got it over here. We'd know that that gives you a -I, so the negation of that would be J cross K. So we're good there, but maybe you want it to be a little bit more obvious. So one thing we could do is switch the order and make it -3K cross 4J negated. And just like we did before, we could factor out the -3 and the +4. So when you pull those out, you're really pulling out a 12. So this is the same as saying 12K cross J, which we discovered directly is -I. And you'd say, okay, well that's wonderful. We want the magnitude of that cross product. Well, this is a scalar multiplier of 12 upon a unit vector of 1. So 12 it is. All right, so the magnitude of U cross V would be equal to -12 scaled upon the magnitude of the unit vector I. So -12 times 1 would be equal to -12, but we want the absolute value of that. So result of 12. Now you could look at it in a slightly different sense, and that would be to say, well, still the same idea of finding the magnitudes, put it in GeoGebra, do it by hand, whatever, find the magnitude of the cross product after you've computed the cross product. It wouldn't be difficult because there's a lot of zeros in this. But if you want to use the new handy dandy formula, you got to figure out the angle separating the two. I hit copy, I meant to hit resize. The angle separating the two vectors, which in this situation it's not difficult. All right, so I'll do a little OR. We know that 0, 4, 0 is along the y-axis. 0, 0, -3 is along the -k axis. All right, so just by doing a quick sketch, you got a vector going off this way, the y-axis, and -k axis going downhill. Pretty easy to see here that we're looking at a 90-degree angle. All right, so theta is equal to pi over 2. All right, so if I want the cross, I would need the magnitude of each. So the magnitude, the magnitude of the cross. The cross, I keep saying cross. The magnitude of each one would be 4 and 3 respectively. So we'd be looking at the magnitude of u cross v is equal to 4 times 3 times the sine of pi over 2. Sine of pi over 2 is equal to 1, so 4 times 3 times 1 gives you a result of 12. All right? That's only easy to do because the angle was easy to figure out. So sometimes it's more beneficial for you to figure out the cross product and then just simply find its magnitude if it's too cumbersome to determine the angle separating the two vectors. All right? So let's take a look at the next one. So again, find a unit vector orthogonal to both A and B. Kind of a hidden question of magnitude here. In order to find a unit vector, you need to divide a vector by its own magnitude. So we need the cross product, and then we need the magnitude of that cross product. All right. So it's just a question of how you want to come up with that magnitude. So if I want, we can flash back here or wherever it is. Somewhere along, oh, there we go. Well, here's one version of it. I mean, it was written somewhere else, but theta is equal to the inverse cosine of the dot product of u and v divided by the two magnitudes. So basically the product of the two unit vectors in the direction of u and v. All right, so that's fine. You can do that. I mean, it's a lot, but it's doable. So in this case, A and B. So we could say A dot B, 0 plus -2 plus -4 is equal to -6. The magnitude of A is going to be 25 plus 4 plus 1. Rooted is going to be root 30. Magnitude of B, 0 plus 1 plus 16, rooted, root 17. So cosine of theta, I'll skip that step. Theta is equal to the inverse cosine. Instead of saying cosine of theta is equal to the dot product over the magnitudes multiplied, we'll just jump right to the inverse cosine. All right, so then to figure out theta, I could do this, but then ultimately, if I want to find the unit vector in the direction that's orthogonal to A and B, I need to figure out the cross product between those two anyway. So that's kind of what I'm getting at, is that, like, we could do all this, but it just seems to be the case where it's probably easier to just find the cross product anyway. But I'm going to continue on. So if I want to find the magnitude of the cross product, what I can do is take u cross v, the formula. Magnitude of u we know is root 30. Magnitude of v is root 17. And so what I would need is the sine of theta. Now the sine of theta is equal to the sine of the inverse cosine of -6 over, so basically all this stuff. All right, so instead of actually finding the angle in radian form and simplifying and maybe doing some rounding, we could figure out the magnitude just by popping all this into Desmos or GeoGebra, whichever you like. All right, so, hello. I suppose if I'm going to go to a web page, I should probably indicate what the web page is going to be. So root 30, root 17, sinus, cosine, inverse cosine, division -6 over radical 30, radical 17, close it up, close it up. All right. Not that it needed to because it already gave us the value. But we get our magnitude of this, about 21.772. All right. So, and if you want, you can just save this as something. Let it be M for magnitude, I guess. M equals. So now if I want to use M later on, I can. All right. So what I need to do is take the cross product of those two vectors, those two original vectors, and then multiply by 1 over this quantity. All right, so I'm going to do a little resizing to create some space. And again, this technique I used to find the magnitude, it was not necessary because we're going to come up with the cross products. We could just find the magnitude of that result in a sec. I just wanted to at least model the one time how to go about doing it using the formula, all right, and how to use Desmos to support your work. So if I want actually U cross V, IJK, 5, 2, -1, 0, -1, and 4. We're finding the determinant of this. So we know that it's going to be in the form of a 2 by 2 square matrix multiplied by I minus a 2 by 2 square matrix multiplied by J plus another 2 by 2 square matrix multiplied by K.
And thank you. make sure you bill me for that.
So we're looking at a 2 by 2 square matrix with components -2, 1, -1, 4, with the idea that if we're looking for the I component, we ditch any row or column that contains an I. For the J, I don't know why I gave so much space there. For the J, we ditch any row or column or row that has oh, I did the same thing twice. The J in it, which would be 5, -1, 0, 4. And then for the K, same deal, ditch the row or column that contains the K. So 5, 2, 0, -1. Diagonal down minus diagonal up, specifically in that order. All right, so 2 times 4 is 8, minus diagonal down minus diagonal up. So 8 minus -1 times -1 is +1, so we're looking at 7I. Diagonal down, 20. Diagonal up amounts to 0, so ignore it, so minus 20J. Diagonal down, -5, diagonal up amounts to 0, so ignore it, K. All right, so put it all together, and you have the cross product, 7I minus 20J minus 5K. If you were to find the magnitude of that, you just rough that out real quick, 7 squared under the radical plus 20 squared plus 5 squared, about 21 and change, 21.77, which is what we got when we used the magnitude of the cross product formula. But here I need the unit vector orthogonal to A and B. So I used U and V over here. I meant to do A and B. A cross B. So if I want to have the unit vector orthogonal to A and B, what I would need to do is take my cross product and multiply it by 1 over the magnitude. All right, so that magnitude I can write in radical form if I want. So I just do the whole thing that I just did here, just get rid of the radical. So 7 squared plus 20 squared plus 5 squared. So 474. We could look to simplify that if we want. 474 divided by 4. No, it's not really clean, and it's not really the best use of time, I guess. At first glance, I'm not seeing anything, but you never know. I mean, I could do the table method, if you remember that, old school. You just do a quick 474 divided by x1 in this case, and just start putting in values. 2, 3, 4, 5, 6, 7. As I look through very quickly here, I'm not seeing anything that's going to help us simplify down. So I'm very quickly losing interest. All right. So we do know that the magnitude is exactly the square root of 474, but it approximates to about 21.772. So what I would do is I would divide each of these coefficients by 474. So 7 over, oh sorry, root 474. So minus, oh, I guess I got to put the I in there, right? Unless I'm putting it in component form. So minus 20 over that J plus, or minus 5 over that radical times K. And so that would be the unit vector in the direction of the cross product.